Okay, hello, good evening. Can you hear me?
Yes, can hear
Yeah,
you. Good evening. Salam alaikum.
walaikum assalam. Alhamdulillah, I'm fine. How about you?
Alhamdulillah, I said that we are struggling to catch it.
Okay, thank you. Okay, just we're waiting 1 minute, then we'll start with the session. So I hope all of you already get the previous material, the practice code and also recorded class. Okay. So after completing the today's session, then we talk about the problem solving for previous classes. Okay. If you have any problem, then we try to discuss about the problem solving class. Okay. So okay, let's we will start our today's session. Just a minute, let me share my screen. So today's session I discuss about the two topic for the soil loss estimation, as well as we also discuss about the NDVI change detection. Okay. So previous class mainly we discuss about that NDVI vegetation trend analysis, how we can easily make the trend analysis, help of man candle or help of linear regression or linear fit model, how we can easily check the trend of NDVI. Okay. Today we discuss about the NDVI change detection, as well as we also discuss about that soil erosion or soil loss estimation. This type of things we try to identify help of remote sensing. Okay, let me share my screen. Can you see my screen? Is it visible? Yeah, is it visible? Yeah. Okay. So today we discuss about that how we can easily make the soil loss estimation, as well as how we can easily make the change detection. Okay. So let me open my slide. So I try to explain all of those step by step. Okay. So basically, in this time, we are just use one model. Okay, it's popular model to estimate the soil loss estimation. It's called the RUSLE model. Okay, so help of RUSLE model, then we try to identify the soil loss erosion. We can easily identify, and further we can also create the soil erosion risk mapping. Okay, suppose you can see this is the map. So in this map we can easily get for we can easily get the idea where is the high soil risks. We can easily get this type of pillars. We find out the high soil risks. Okay, you can see this type of red color. Okay, so more than 40 ton per hectare per year. Okay, this is the unit, ton per hectare per year. And this type of yellow color indicating about that very high, then high, moderate, or slight. So after creating the RUSLE model in Google Earth Engine, so further we simply download the GeoTIFF file format in just importing the ArcMap to produce this type of map. Okay, so we can easily do it after downloading the final GeoTIFF file format, then we can easily use it. Okay, And in the RUSLE model, we can use some data. Okay, we can use some data factor we need. So we need the soil data. Okay, then we need the rainfall data. We also need the dam data. Okay, then we need the land use data. Okay, so this type of data we need. So now we can use the different sources for this type of soil data, rainfall data, dam data, or land use data. So we can use here the different types of sources. Okay, and when you select the source, you try to use the high resolution sources. Okay, to get the more better soil loss erosion mapping. Okay, in this case, rainfall data we can easily get from the chart satellite imagery. Okay, chart satellite imagery or GPM, global precipitation measurement. This satellite we also find out the rainfall data. But this type of data, when you work with a small study area, then we face some problem because it's not the good resolution. This type of chart satellite image or GPM satellite image, this pixel size is very high. Okay, so this is the main condition. When you work for your own research work, you try to use the high resolution satellite imagery for this type of data source. Soil data, rainfall data, dam data, or land use data, all data try to collect from high resolution satellite sensor. Suppose for the rainfall data, you don't have any, suppose you just use simply use the station data. Okay, simply use some station data. So from the station data, just use and then create the IDWI, mainly interpolation IDW, and then you can easily create the rainfall map. Okay, we can easily, then it will be more high resolution. When you apply the station data and make the IDWI map, then we can get the very high resolution rainfall map. But when you use the chart satellite imagery or also use suppose GPM satellite imagery, so this type of satellite imagery is not good resolution. Okay, so that's why when you use this type of data, then you don't get the better map for the small study area. Okay, but in the large scale, we can easily use this type of data. Okay, this large scale we can easily use this type of data, subs data or GPM data we can easily use, and further we can easily calculate. So now what I need, if you check for the soil data and every data set, I need to calculate some factor. Okay, and this is the main equation for the RUSLE model. So basically RUSLE model is one of the most widely used empirical model for estimating average annual soil loss. Okay, average annual soil loss we can easily compute by RUSLE model. And here we just use some factor. Suppose we can see, we find out the K is one factor, then R is another factor. Mainly K, it's called the soil erodibility factor. Then K mainly K soil erodibility factor. Then we find out the R mainly rainfall erosivity factor. Okay, and then also LS basically topographic factor, mainly slope length and slope steepness. Okay, and C mainly cover management or land use land cover management factor, and P mainly support practice factor. So this type of factor, first of all we need to compute. Okay, and then we simply multiply, you can see all of multiply, then we find out the A value or area. Okay, so then this unit is the ton per hectare per year. So then we try to use the yearly data. Suppose we just make the yearly data for rainfall, yearly data for soil data. So all of data we just collect for the yearly, and further we simply create this type of factor. Okay, and then just multiply the all of factor together. Then we can easily estimate the soil loss. Okay. So and further we also compute the area. So I'll also try to show you this type of process, how it will be work practical. Then you can easily get the idea how we can easily apply the soil loss estimation for any specific boundary. So now basically RUSLE model, it's a revised universe soil loss equation. Okay, and estimate the average annual soil loss ton per hectare per year, and it mainly focus on the sheet or reel erosion. Okay, sheet or reel erosion it mainly focus, and widely applied in the agriculture or watershed and land management. We use this type of map. And in the RUSLE equation, so this is the main equation. You can see this equation basically R mainly rainfall erosivity, then K mainly soil erodibility, LS mainly topography, okay, C mainly cover management, and P mainly land use and practice, land use practice or land use. So this type of factor we need to compute and then further simply multiply all of those together. Then we can easily get the result for soil loss estimation area. We can easily identify. And if you check, this is the follow chart for this work. So we need this type of factor, rainfall factor, then rainfall from for the R factor, it's come from the rainfall data set. K factor, it's come from the soil data set. LS factor, it's come from the topography. C, it's come from the land use, power management, and P mainly practice or land use. It's come from here. So all of data we just need to collect, and further we can simply apply this formula. Okay, from the DEM we can easily calculate the LS, rainfall we compute the R, soil map K, satellite data for NDVI we just use for the C, and land use land cover for the P, or practice land use land cover. So now what is the R factor? R factor, it's indicating about that your rainfall erosivity. Okay, erosivity basically it's quantify the erosive power of rainfall, and it depends on the rainfall intensity, amount, and duration. And high intensity storm generate higher erosivity. Okay, and open we are just use different types of data such as chart satellite data or also TRMM data set. Okay, so this type of, so let me try to explain, open my code and try to show you that it will be more better. And you can get the lot of paper that already work with the RUSLE model, and you can get the all of those more better. So let me open a code editor. Okay, okay, let me open some paper, just a minute. So this is the one kind of paper for soil erosion in the coastal region of Bangladesh. And in this paper, so this is the study area they take, and further there you can see compute this type of factor. You can see for the LS factor, it's come from the digital elevation model or DEM data. The land use land cover, it's come from the C factor. Okay, then you can see they are also use some data from the existing literature they use, and then use some data set. And precipitation database, mainly rainfall erosivity, they are also used. And also take the soil data from FAO, this data source, and they take the K factor. Okay, compute the K factor, and further just simply compute all of those and apply the soil erosion map using the RUSLE model. Okay, you can see this is the main equation, and they calculate the, so you also try to read this type of paper, then you can easily get the theoretical information, what is the rainfall erosivity and how it will be worked. Okay, so basically erosivity, it's quantify the erosive power of rainfall. Okay, and this power is depend on the rainfall intensity, rainfall amount, or rainfall duration. Okay, and high intensity, because high rainfall intensity, it's indicating about the storm generate for higher erosivity. And this rainfall we can easily compute. You can see that also put all of those is for that R factor they calculate. Okay, all of those energy or multiply the maximum 30-meter intensity. Okay, and slope condition, climate factor, so then you can get the more better idea. And you can see this is the formula. Okay, they are using here for the rainfall erosivity, that use this formula. So R equal to 38.5 plus 35. Okay, this is the P mainly precipitation data or rainfall data. Okay, so here P denote the total annual precipitation, it's the total annual precipitation or rainfall in millimeter unit. Okay, so this is the one equation we find out in here. So this equation basically identify for rainfall erosivity we find out. Okay, so if you want, you can also use this equation and then also compute the rainfall erosivity and also mention the paper citation, there is no problem. So if you want, this is another, it's a soil erodibility factor. So basically soil erodibility factor, it reflects the susceptibility of soil particles to detachment and transport. Okay, suppose influenced by the soil texture or organic matter or structure or permeability. So this type of influenced by the soil erodibility. Erodibility basically the susceptibility of the soil particles to detachment and transport. And sandy soil, we find out the low K value. Okay, for the sandy soil, it's this value is the low, and silty soil it's the high. For the K factor we find out the or high soil erodibility factor we find out for the high in the silty soil, but sandy soil we find out the low erodibility factor. So you also try to read this type of thing, then you can get a lot of information about this type of soil eroding factor. And you can see they use this type of soil acronym they use, and the K factor value for G this value. Okay, so this is the one another factor. And then you can see the another factor for the crop and management factor. Okay, or cover management factor. So basically this is the ratio of soil loss under the specific vegetation by management to that bare soil, that of bare soil. Okay, and range from 0 to 1. Okay, 0 mainly dense forest or no erosion, because in the cover management, suppose I have a vegetation area some, so this vegetation area we consider it there is 0 mainly no erosion. Okay, we just compute the erosion for our bare soil land area. And this C factor or cover management, it's mainly ratio of soil loss under the specific vegetation to that of bare soil. And range of the C factor, it will be dense 0 to 1. 0 basically dense forest mainly no erosion. To 1 mainly bare soil or maximum erosion. Bare soil we find out the maximum erosion, and dense forest we consider the no erosion. So for the C factor or C cover management, we are just use here the NDVI. Okay, we can easily compute the NDVI and identify suppose dense vegetation or bare soil. So this type of dense vegetation, there is no erosion, but bare soil maximum erosion. It compute the C factor or cover management. It's indicating about that. After that, you can see they also use the C factor value. You can see for the bare land, it is a C factor value, rain fed cropland, then different types of, you can see tree cover. So it's a defend, but this value range will be 0 to 1. Okay, 0 to 1, but we find out the bare area, it's very high value. Okay, bare basically 1 mainly bare soil, and in the bare soil we find out the maximum erosion. And dense vegetation or dense forest, no erosion, low value, very low value for cover management or C factor value. Okay, then if you check, we find out the another factor, it's called the LS factor. So LS factor basically it's a topographic control on erosion. Topographic control on erosion. And in the LS factor, basically L it means that your slope length. Okay, slope length. And S for slope steepness, and L for length. Okay, length and steepness. Basically length, it's the longer slope allow more runoff, mainly more erosion. Okay, suppose I have a very long slope or high slope. This high slope, what happened in the high slope, we find out that high runoff, okay, or more runoff, and this more runoff indicating about the more erosion. Okay, and low slope indicating about the low runoff, and low runoff indicating about the low erosion. Okay, so this is indicating about the slope length, because soil erosion is also different on the slope length. Suppose my slope length is very high or longer slope allow more runoff, and we find out the more erosion in the longer slope area. And slope steepness Basically steepness, it indicating about that steeper slope increase runoff velocity. Okay, suppose steeper slope increase the runoff velocity and more erosive power. This type of slope steepness, suppose I have a region there the steeper slope is very high, okay, or steepness is very high, so then it increase the runoff velocity is also high, so then the erosive power is also high, we find out. So this type of LS factor, length of slope, or also steepness, we can easily generate from DEM data. From the DEM data, we can easily generate this type of factor. Okay, using the NASA SRTM DEM, we can easily compute, and further we can easily identify slope length and also slope steepness. Okay, then what factor? We can see the another one is for P factor. P factor basically it's called the support practice factor. And support practice factor, it measures the effect of conversion practice. Okay, it measures the effect of conversion practice, and it ranges from 0 to 1. 0 to 1, mainly lower values equal to more effective practice. Okay, and typically as I'm using land use land cover maps, we are used for the slope categories. Okay, so just we are use the land use land cover and we category some slope category and identify the P factor or support practice. Okay, so you can see for this slope 0.0270, this P factor mainly 0.55. For this slope, this P value. Okay, also you can see for this slope, this P value. Okay, it's depending on this type of slope range. So this type of factor we need to calculate one by one, and then we can easily apply. So let's go practically discuss, then you can easily get the idea. But this type of RUSLE model is not work for all region, all erosion it cannot be computed. Suppose in the gully erosion area, we cannot use it. Okay, in the gully erosion area we cannot use it, this type of model, and it based on the we are just others, it also work, there is no problem. And sensitive factor mainly R and K factor, we find out that it's more sensitive factor for parameterization. Okay, otherwise we can also apply it for any others, no problem. Okay, so let's go try it one by one. I try to discuss, then you can get the idea. So you can see basically in this paper they are take the satellite, they are use the station wise data. You can see this is the latitude, longitude, and also take the rainfall data. Okay, and this is the latitude, longitude. In this time they are not use the chart satellite data, or they are not use the satellite data, they use the ground station data. Okay, and further this type of data just apply the IDWI, and further they also calculate the erosivity, this type of then calculate it. Okay, also you can see for the soil erodibility factor. Okay, also you can see topographic LS factor, the cover management factor, and you can see they create this type of C factor map. So just simply create this type of map in the arc map for the map layout, and further just represent all of factor and find out the potential soil erosion factor and make the class, and also identify the area. Okay, and then finally finish. So this is the one kind of paper. So if you check lot of paper, you can easily find out for the RUSLE model for soil erosion. So you also try to read, I also send you this type of paper link, so you also try to read all of paper, then you can get a lot of idea about that RUSLE model. Okay, so let's do now practical example. So let me open, okay, I already opened my code editor. So first of all, I want to work, suppose I want to work a basin area. Okay, hydroshed basin area for Bangladesh. I want to identify soil erosion, okay, in a basin area, river basin area. Then it will be work more better for the river basin area. So now how I can take the river basin? So there are a lot of way, we already know for the how we can easily calculate, make the river basin or identify catchment area of this basin. But in Google Earth Engine, you can also use some ready-made data set. It's called the hydrosheds data. If you simply search on the Google, suppose hydrosheds, so then we can easily get this website. This is the hydroshed website. So from here, we can easily get the hydro basin data or also river data. Okay, different types of product we can easily get from the hydrosheds.org, this website. Okay, you can easily get this type of things. But if you want, you can also create the basin area from the DEM. It also possible. Suppose I have a DEM data, so this DEM data I just use, and further I from the DEM data I can easily identify the suppose basin area. I can easily identify basin, as well as I can also create the catchment area or basin area, or we can also get all of those different types of hydrological parameter we can easily generate. Okay. Okay, so this type of hydrosheds data is easily available in the Google Earth Engine. If you simply search here hydrosheds, so you can see different level for the hydrosheds, level 1, level 10, level 11. So different level you can easily find out in here. Different basin level you can see. Okay, suppose I want to work with for hydro basin level 4. You can see this is the hydrosheds basin level 4. So this is the hydroshed is the mapping product, provide the hydrographic information of regional and global scale. So this is the one kind of data set. So from this data set I can easily use the, you can also filter the data set using the high bus ID. Okay, so let's we try to use this data, and further we simply choose a hydro basin. So just click on here. So now how I can filter my own hydro basin area. So further I simply copy their code. Just copy and paste here and run the code. So now it's added all of hydro basin area. It's globally available. We can easily use it. Suppose I want to work for Bangladesh. Just open. Or you can also take the more local hydro basin also. There is no problem. Suppose you can see I in the Bangladesh, I want to work for this. I want to work for this basin. Okay, for the hydro basin I don't use, or for this. Okay, it's covered this full river. So I want to use this boundary. You can see this is my hydro basin boundary. So I want to use it, and further I want to identify soil loss for this study area. Okay, so now I want to filter this boundary. So how I can filter? So for filtering, you can simply click on inspector tab and click on this boundary. You can see just I click. So now it provide me all of information for filtering. Okay, for this basin. So if you check the object from the properties, so you find out where is it. Bands type image. Okay. Okay, I just let me print or run the code again. Just a minute. I think some problem. Or refresh my. Okay, refresh. Take a new code editor. Just I copy and take a variable, suppose data set, and store it, this data set. Okay, and then I want to add the layer, suppose snap dot add layer, and just copy. I think some networking issue, that's why it takes some time, or it's not connect the Google server properly. Yeah, so now it's worked. Okay, so now you can say I want to work with this basin area. Okay, so I want to work with that, or just click on the inspector tab and click. So now you can see it provide the all of information for filtering this basin, and this is a level 4 basin. If you want, you can also use the more local, then also increase the level 5, 6, 7. Okay, so just I use it. You can see we find out the all of properties. So from the properties you can see different for filtering. I can easily use the high bus ID and filter and select this my study area. Okay, I can also use the main bus, this number, and filter. So about then to use the high bus ID and filter my study area. So for that, just use here, take a variable, suppose ROI equal, and call this data set. So this data set I want to filter. So just put here the filter. Then how I can filter? Earth engine filter dot equal this high bus ID. Just I copy and also put here this value. Okay, this is my high bus ID value for this basin area. Just I copy and paste here. Okay, so just simply filtering my study area. So now I want to add the layer. So just put here map.add layer and call the ROI. So now it's not need. Just run the code. So now I can easily find out only for this boundary. Suppose this is my boundary. So for this boundary, I want to compute the soil erosion or estimate the soil loss. So after doing this thing, select the study area. Then we just need to work with rainfall, mainly R factor. Okay, we'll discuss about what is the R factor. Just compute the R factor. Okay, R factor. So for the R factor, it also better. You can use the station data, okay, to get the more better map. But in this case, I just use the satellite data. But it's better to use. You can see the maximum paper they are used at the station data to produce the R factor. Okay. So for the R factor, I want to use here suppose charts satellite data, and the precipitation data for the charts. I can just use here this from the charts. I just use okay. You can also use the panted or daily, no problem. Suppose I want to use suppose panted charts panted. So this is my rainfall data. Just I copy. So station data source basically you can get the data from your some country, your country, suppose weather, government website. We can also get this type of data. Okay, this type of station wise data they also provide some data. Suppose if you check some, suppose I simply search here PMD, Bangladesh Meteorological Department. So you can easily check, you can easily get some data for our region, suppose district or division. Okay, we can easily get this type of rainfall data or precipitation data from this type of uh, meteorological department website for a specific country. Then we simply use this type of data and then make the rainfall map using the station data. Okay, so it's provide that you can see this is the Bangladesh Meteorological Department. So from here you also get a lot of data set. Suppose, okay, let me open it. So you can see we can get, so we can easily get this for this study area. You can see for this study area we find out the 51 millimeter rainfall, wind speed 6 kph, humidity 9%. So and also you can see this place, this place, this place, this place, this place, this place, this place. We can easily get. Yeah, it also available. Okay, simply search, then you can easily get this type of website. Not only for that, we also get some. Suppose click on here for this study area. It's loading. Or we also get the radar imagery to get the precipitation. You can see in this time here we find out the, this is the date 25/09/14, and you can easily choose our division. Okay, suppose in the Mymensingh division I need to choose suppose Netropona. So now we can get the result for this district. Okay, also you can see the rainfall bar graph. Further this type of data we just use and then just modify this type of data. Also you can see the landslide warning. So you can see we can get, this is our map for the landslide warning place. So in this place you can see we also get the precipitation. Okay, so you can see for this place it show the precipitation 14 September, 15, 16. So it will forecast. We also get this type of here. Suppose last 30 days you can try to check or forecast. You can see the forecast. We also get the forecast also for every day. We also get from here for this landslide zone. Also weather chart. So also try to find some simply search, okay, for your own country. Then I hope it also available. We can easily get, okay, this type of information. Okay, so just in this case we try to use the SAP satellite data and identify the R factor. So I simply copy the charts painted. I want to use this data because it's available from 1981. Just I copy the snippet ID and take a variable. I can put the variable name, suppose I put name suppose charts. You can put any name and paste here. Okay. And these charts I want to filter. Okay, so in this case suppose I want to filter this time, filter date. Okay, and I suppose I put the time year of 2017. So was 1st January. I take the 1 year annual total precipitation. So 2018 01 0. So it's covered the 2017. So I take the 1 year data and further I need to select the band. So select the band of if you check this band name is if you check where is the band name, precipitation. Let me open. You can see the band name is precipitation. So my formula is that I need to compute the total precipitation in 1 year. So just I paste here this band and then calculate the total. So put here the sum. And I think some problem for my server on Google Earth Engine. So that's the reason this type of function show the normal color, but it showed the purple color. So it is the problem for the server or network issue. That's the reason it not show the purple color. It show the normal color. So I compute the total precipitation for 1 year or annual precipitation, and then clip with my study area, which is ROI. So just I put here the ROI. So now we try to add the map of total precipitation. That was mapped to red layer. I just call the charts, copy and paste and run the code. So now it's added the total precipitation map for this place. If you want, you can also add here the color to display the map. It's optional. Okay, so I'll try to show you the add the color, but you ignore this part, there is no problem. So let me try just add here, and then we just try to apply, suppose low precipitation area, show this type of color, better than show this type of yellow color, then suppose green color, and high area it show this type of color, and apply. So we try to put, so we find, you can see this type of map we find out. Okay, so this type of green blue color indicating about the high precipitation area, and you can see we find out this type of grid or cell. Okay, because this resolution is not good. If you check what is the resolution of the data set, it's the 5566 meter. So that's the region. When you try to make the rainfall, annual rainfall, try to use the ground truth data, then it provide you with a more better map for the rainfall. So now this map I want to use and compute the rainfall, mainly R factor we need to compute. Just import the data, just copy the visualization and put after the object, and put the layer name, suppose if it's a total rainfall. So you find out. So after computing the total rainfall, then we need to compute the R factor, help of empirical linear model. Okay, so now we have just use the empirical linear model and then identify rainfall erosivity we try to compute. Okay, so if you check in this paper for the rainfall or R factor, they use this equation. Okay, so if you check some other paper, they also use the other factor, other types of variable. So basically these things they are compute, okay, using the empirical equation. Okay, empirical linear model they are apply, and further they are use this type of equation, this type of, you can see 38.5 or 0.35, and you can also read this type of thing, then you also get the idea. Okay, so they also make the citation, this type of citation they are used to determine the R factor for the coastal zone. Study utilize the equation, you can see, which provide the erosion index values for the region as studied by, this is the citation. Okay, so then you can get the idea where they come from, this type of equation. Suppose I want to use it, or if you want, you can also use the other equation, then simply cite it, this type of things. So this is the it also work for the coastal region in Bangladesh, and now I also work with for Bangladesh study area. So I think this equation is also better work for my study area. Okay, so when you work, so you try to check some previous literature or previous scientific paper which already worked for your own study area or your own study area for the different place, then try to use this type of paper. So then we find out the more better result. Suppose now I want to implement this equation to compute the rainfall erosivity. So let's we try to just copy, and this equation I just simply connect with my total rainfall. So basically this is the equation. So here it's a 35p. So basically this p is for annual rainfall, okay, and this is the constant value. Simply multiply and add. So take a variable. I put the variable name, suppose r equal. So I want to apply it. So just I call this map, or it's a image. So just I copy and apply ee dot image, and I just call this image, just copy and paste here. So this image I want to multiply. So just put here that multiply with this value 38.5, and then add with sorry, it will be 0.35, okay, 0.35, and then add with this value 38.5, okay? And I rename it. Suppose I put the dot rename it as a r. Now if you want, you can also add here the r factor, r map or erosivity map. So simply add map dot add layer and call the r. So now run the code. So now you can find out the erosivity map. Where is the high erosivity, where is the low erosivity, then we can easily get this type of idea from this erosivity map. Okay, so this is the done for r factor. So now for the we talk about the k factor. Okay, if you want, you can also add the color. It's not mandatory, because this type of file we also need to download the GeoTIFF file format, and further we are just use the ArcMap to produce the map for our research paper or presentation using the ArcMap software. So in this time it's optional, not need to visualization. So I try to compute, suppose, k factor. Okay, so in the k factor we just load the soil data. Okay, so this soil data we need to compute. Okay, so in this case we try to apply the soil data, and in the soil we are just use the soil texture data. Okay, if you want, you can also use the soil organic data. If you check the paper for the k factor, it's mainly soil erodibility. Okay, this soil erodibility we can also use at the soil different types of soil data. Suppose soil k factor, we can use the soil texture or soil organic matter. So this type of things we can easily apply in here and identify the soil erodibility factor. Soil erodibility factor, it reflects the susceptibility of soil particle to detach and transport. Okay, and this soil erodibility factor or k factor, it's depend on soil texture, then organic matter, then soil structure, and also soil permeability. So this type of things also depend on the soil erodibility factor. So from here we can use any factor, no problem. Suppose in this case in Google Earth Engine we can easily find out the soil texture data. Suppose I want to use it. So for the soil texture data, I simply search here soil texture. So basically this one, open land soil texture USDS system. If you check the data set, so we find out different depth of soil data. You can see soil texture. This is the 0 centimeter depth. Mainly we try to use this B0, is indicating about the 0 centimeter depth. Okay, B10 basically it is the 10 centimeter depth of soil texture, then 30 meter, then 60 meter, 100 meter depth, and 200 meter. We find out this type of things. And you can see we find out some soil texture for, you can see, so it's different types of soil texture name. You can see this type of soil texture for that 0 centimeter. Okay, in the 0 centimeter we find out this type of soil texture. If you get this the more information about this type of description, so you can simply search here, suppose simply search here soil texture open land data. Or information, just click on here soil grid global grid soil information. Soil grid global grid soil information data access. It's not loaded. Why? Okay, opening. So you can easily get, you can see. So this is a soil organic carbon stock. You can easily get the for each soil. Okay, it provides a lot of data from this website. You also get the soil grids.org. It provides this type of data. You can see the depth, and also this is the legend. Okay, 0 to 30 meter depth and ton per hectare carbon stock information. And if you simply check the these properties, soil organic carbon stock and organic carbon density 0 to 5 centimeter, okay, it's available. And once again the physical, so you can get this type of information: bulk density, clay content, okay, quartz fragments, sand, silt. So you can easily choose this type of thing, then it creates this type of data. Or water content, volume of water content of soil, okay, volume of water content. So this type of data we also use the different remote sensing analysis. Okay, and we can easily download this type of data from here. Or you can see the chemical soil, we can easily get the this type of data, the nitrogen, soil organic carbon, also pH of water, we can get this type of data. Okay, also soil class, if you check the soil class, so you can see the world reference based soil class 2006 group. We get this type of soil class. Also you can see the soil profile. Okay, so at day by day it also added different types of data. We can also explore for a specific coordinate. Also you can just put the coordinate, we can also get the data. And you can simply download this type of soil grid. Okay, simply suppose which layer you want to need, just simply select. Okay, calcium carbonate, okay, or organic carbon, or PSS2O, or total carbon, just simply choose. And you can see the format which for it, you can simply download the shape file. So this shape file you can easily use the arc map and produce the map easily. Okay, and also geo package or GeoJSON or CSV format data, you can easily get this type of download the data from here. Or if you want, you can also put the specific latitude longitude value, minimum and maximum latitude, and also download the data. So this is the one kind of website we can also download the data, different types of soil data. Okay, soil organic data you can easily download from this type of website also, or organic carbon density. Okay, this type of thing you can easily download from here. Okay, okay, so you can see now I want to use this data, soil texture. and this texture I need to use the 0 centimeter depth. So for that, simply just copy the snippet ID and paste and paste. And give a variable name. Suppose I put a variable name soil. Okay, and this data I want to display, suppose on my map for soil texture map. So just simply click with my study area, which is ROI. Okay, and I want to add the soil texture map. Okay, and we need to select the band because I want to choose 0 centimeter depth. So put here the dot select and put the band name. So my band name is if you check the band name, B0. Yeah, so B0, this one. So now run the code. So we find out, you can see this type of if you are also just suppose let me just print and show you that soil just run. So B0 class name, or when you download this GOT file format, then you can easily get. Okay, so all of soil texture which are available. Okay, and further from here simply write the name. So this soil texture, this name, this soil texture, this name, just export the GOT file format. Okay, then it will work. Okay, so now we just create some, we need to compute the soil. This is the soil data. So this soil data we just use and apply the soil erodibility factor. Okay, so erodibility factor, how we can compute using the soil texture. So in this case they are used this type of formula, you can see. Okay, for the soil erodibility factor, and you can see they are used this type of factor. Okay, k factor value, it's constant for this type of soil, but in this time we are not use the soil. This is another data of soil. Okay, but we are just using the soil texture. Okay, I think. Okay, you can see soil erodibility factor was calculated this equation, Williams equation. Okay, they are apply the Williams equation and further they compute the k factor computed. Okay, for there, and use here the soil particle eroded. Okay, sediment, silt and clay particle, commonly actually soil erosion, silt and clay, these two particles mainly commonly for. Okay, and also runoff plot the measurement, use the calculable factor k, and they are use the Williams soil texture categories. Okay, they are use the Williams soil texture categories and organic matter content. Okay, to determine the k factor. Okay, okay, they use the Williams soil texture category and organic matter contents to compute the k factor. Okay, so let's try to apply. just okay. So in this time, we just take a variable. Suppose I put a variable name is k, and I just call the soil and apply the expression. And in this expression, we just compute this type of value, simply input in one by one. Okay, kindly refresh and join again, then it will be okay. So we simply set, suppose I put a
I don't know if it's just from my end. The connection seems to be having issues.
can you see my screen or not? No. Okay, I hope it's okay. You can see my screen, yeah. Okay, so I just put the P. I take the P, and from here I simply apply the soil. I can close this bracket. Less than, I put the suppose 11, and I put the value. Suppose 0.053. Okay, for the first classification of soil erodibility factor value, I simply set this value. So you can also put the any other literature and also use the other value. Okay, but I set this value 0.053 for the first classification. Then use this same process and we create for the different value for the different classification. So we try to create total 11 classification, okay, or 11 classes we create. So let's we try to apply one by one. So just I copy the same line of code. Was 2, then 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, can you hear me?
Yes, we can hear you. We can see
Okay.
the screen.
Okay, so we try to create total 11 classes. Suppose from, and we'll change the value. Suppose first one is 11, then I put here that it's a 10, then I put here suppose it's a 9, then it's a 8, then put here the 7, 6, then 5, then 4, 3, 2, 1. I create another class, suppose it's 0. Okay. So we just put there, but it show the problem. This problem is that we need to apply the plus sign. Let's put the plus. Okay, but this code you can also write the another way. This is the another way. We also write this type of classification. Set some specific value, okay, and make the classification. So this is another method to add. Okay, so that's okay. And we set the value. Suppose second value, I simply put here 0.0170. Okay, second and third value, suppose I put here 0.0 0.045 for this class we set. Then suppose 0.0, suppose 50. Then put here the 0.0499. Suppose 0.0394. 0.0, suppose 264. 0.0423. 394. That was 36. And finally I put here suppose another class for 0.0341. And finally 0.028. Okay. So if you want, you can also use this type of range and also make the classification total 11 class. Or if you want, you can also use suppose this paper they are use this type of range. Okay, you can also use this type of range, but for that we need to use the soil organic matter also. We need to combine the soil organic matter data also for this. In this time, this is the Williams equation. So this is the Williams equation that apply and compute the soil erodibility factor, help of soil texture and also soil organic matter they're including here. Okay, you can see the organic carbon, then clay fraction, then sand fraction, then compute. Okay, but we try to apply this type of method to compute the soil erodibility factor from our soil data. We simply search some classification. Okay, suppose this type of soil texture, we simply make some classification, and further we have just put here suppose dot rename, and I rename it as a k factor. And this thing just we already use the clip function. So let me add suppose map.add layer and call the k factor, then check what happened. Just put the k and run the code. Oh my god. Let's show a problem. This problem is image phrase expression. Image phrase expression, we have some error at the character 30. I create the last class, suppose only for 0. No, it's not going to show the problem. Just let me open my previous code and show the solution. K factor. Yeah. So K factor. Okay, let me copy and just paste and run the code. It's a ROI. This is the band name. Okay, so now if you check, we find out this map K factor. This is the K factor map. And if you check, we set the 0, 1, 2, 3, 4, 5 up to 11, because if you check our data set for the soil texture, in the soil texture for the B0, this for this band, we find out the total. I can see we take for 0 to 11. 0 to 11 means that 12. So we take this 12 class. And for this type of texture, have a value. Okay, so this value is simply set in here. Suppose for the 11 number class, this is the value. Okay, for the 12 number class, this is the value. For this class, this is the value. Okay, so I can simply check some literature, then you can easily get for the specific soil texture, we find out this type of value. Okay, suppose you can check in this texture for this CL, this one kind of texture. So for this texture, we need to set a value. Then for this texture, we set the value. So in this case, we find out total 12 class, okay, of soil texture. So for the 12 class, we try to set the 12 value, okay, and calculate the soil erodibility factor. Okay, I hope you also get the idea how to work. Yeah, so this value we can easily get some literature or some research paper, you can easily get it. Okay, and now we simply make the classification for the, suppose this, for this 0 number soil texture, we set this value. For this 1 number soil texture, we set this value. For the 2 number soil texture, we set this value. For 3 number soil texture, we set this value. We simply set this type of value, and then we find out this type of soil texture, mainly soil erodibility factor, mainly K factor map or soil erodibility map, we can easily generate. this way. Okay, so I hope also get the idea how it will be worked for the K factor. So on K factor, basically it's also influenced by soil organic matter or others. So if you want, you can also add this type of data, and you can also work with the soil erodibility factor. You can also compute not only for the soil texture. We can also use the soil organic matter or soil permeability. If you have this type of data, suppose permeability data for the soil, you can also use this type of data and identify for soil erodibility factor. Okay, erodibility factor you can easily identify. So this is a soil erodibility factor we can easily use, and we can easily identify the soil. You can also use the soil organic matter. So a lot of data, so we also get the soil organic matter. Okay, so basically soil texture, then organic matter, then soil permeability data. So basically it just indicating about that your soil particle detachment and transport subsibility. Okay, so here is the transport or detachment is very high. If you check this map, just I will show you that from the visualization. This is, so it's loading. I think some networking issue, it's loading. Hello, can you hear me? Okay, so if you check, we find out this type of map, basically this type of color indicating about the high soil erodibility. It's a low, so it's a low, but this type of color indicating about that very high. So it's a show the, sorry, low soil erodibility. So let me just stressing and show you the result, and it look more perfect. Okay, so let's go. You can find out this type of place. If you check this type of place, it show the very low soil erodibility, because this place, if you check, we find out this place have a some water body. So this type of water body, there is very low soil erodibility because there is not what soil. So that's why you find out it's very, it show very low value. We find out the very low value. Then you can see we find out the some yellow value. Okay, so soil erodibility factor, it's indicating about that susceptibility of soil particle to detachment and transport. Okay, so you can easily find out this type of have the bare soil or others. So it easily high susceptibility for this type of soil. We find out the high susceptibility for the detachment or also transport. Okay, that's why we find out the K value is very high for this type of place. But if you check this place, we have some water body, so that's why it show the very low soil erodibility, because it's a water or others. So that's why we find out this type of color. But this type of color indicating about the high soil erodibility factor, because it's a bare land or sandy land, we find out in here. Okay, can you hear me? Yeah, can you hear me? Okay, it's some networking issue, so I hope now it will work. Okay. So you find out, you can see this type of place is the high soil erodibility. It means that for this type of soil is the high susceptibility for detachment and also transportation. This type of color indicating about that. Okay. So this is the K factor. I hope you also get the idea how to calculate the K factor. Help of soil texture. If you and can also use the soil organic matter. So using the different types of literature, you can also find out different method to compute the soil erodibility factor. Okay. So now we talk about that LS factor. How we can easily compute the LS factor. So LS, basically in the LS factor, we compute the two things. One is the slope length. Another you compute for it's called the slope steepness. Okay, slope length and slope steepness we need to compute. Okay. So let's try to compute the slopeness and slope steepness, and it's called the your LS factor. Okay, it's called the LS factor. So for the LS factor, we are just apply help of DEM data. So we can simply import the DEM data, NASA SRTM DEM. I simply search here SRTM. You can see SRTM data, NASA SRTM DEM. Okay, this data set I want to use for computing the LS factor, slope length and slope steepness. It's called the L and it's called the S, mainly LS. Okay. So take a variable. Suppose I put the variable name is that elevation, and I just put here this DEM data. And from the DEM, we simply select the specific band, whose name is the elevation. This is our band name, elevation. And now it's just clip with our study area, which is ROI. If you want to also display the data, suppose just map.add layer and add the elevation for your study area. Just like copy and just display the elevation. So now I find out the elevation map. Where is the highland, where is the lowland? We can easily get the idea from this map. So it look like that. We try to add the color. Suppose I just stressing 98%. And I put the suppose lower elevation, show this type of blue color. Greater than high, so this type of green color. Then I put this type of yellow color. and high elevation show this type of red color, and apply. So now you can easily get the elevation map. You can easily get where is the high elevation, where is the low elevation. You can easily get. Just copy and paste after the object name. I put it say elevation map. Okay. So now we find out the elevation. So from this elevation, you need to compute the slope. Okay. So take a variable, suppose slope 1, and then I put call ee dot train dot slope. I want to compute the slope using the elevation data. Okay. Now if you want, you can also display the slope map. Okay. Or this slope, it's this unit is the degree. Okay. Degree. So now we need to convert the unit, convert this unit into percentage. Okay. So percentage we need to convert. So take a variable. That was I put the variable name is the slope, and call this slope 1, which is stated the degree unit. So this degree unit I want to convert. So for converting the slope degree to percentage, just use the formula divide 120 180 these things multiply with pi value. We can also write here suppose math dot pi, okay, and then 10, and these things just simply multiply with 100. So now it's converted into degree. So just I want to add that this slope now work as a degree, so percentage. Find out this type of slope in percentage. If you want, you can also add here the color. It's optional, not need to add. So we find out this type of slope in percentage unit. Okay, so now we compute the slope ls for the different level. Suppose I want to add for the ls 1 to ls4. Okay, all of ls or length of steepness and length of slope and slope of steepness. So we compute it. So for that, first take a variable, suppose ls4. So I need to apply formula. This formula it call that square root. So just I call the math function. So math, from the math function or math library, I just use the function of sqrt, square root. Square root of this formula is 500. Its formula ls4. Then take the another variable, suppose ls3. In ls3, we simply call the slope, basically this percentage of slope. So it's a image, so that's why I just apply ee dot image function and call the slope. Okay, call this slope, and this slope need to multiply 0.53 this variable. Then we find out the ls3. So now ls2, take another variable, suppose ls2, and apply ee dot image, call the slope again, just copy the slope and paste here. Okay, this slope multiply ee dot image, call this slope, and these things multiply with the value 0.076. And finally ls1, so take a variable ls1 ee dot image, call the slope, sorry, call the ls3 because we already computed ls2, just call the ls3, this ls3 add with ls2, and add the constant value 0.76. And finally ls, so take a variable ls, and this ls we simply just call the ls1, so ee dot image, this ls1 multiply with this formula, multiply with square root of 500 by 100, so it is stored in the ls4, just I call the ls4, then it will multiply with that and rename it as a ls. So now try to find out the ls factor, just we try to add, suppose map.add layer and call the ls and run the. So now you find out that slope length and slope steepness, okay, and longer slope allow the more runoff. Suppose I have a high slope value indicating about the more runoff. So let's go try to identify this. Also just I put the 98% and I put here suppose low slope ls value show this type of blue color, greater than high show this type of green color, then suppose this type of yellow color, and higher ls value it show this type of red color. So now apply and also import. So now you find out this type of map, you can see, so this type of blue color indicating about that your lower slope, okay, low slope value, low ls value or lower slope, okay. So in the lower slope, this type of blue color it show the lower slope, so that's why we find out the low runoff for this type of slope. But this type of red color, you can see this type of red color, it's indicating about the higher slope, okay. In the higher slope we find out that high runoff, and high runoff indicating about the high erosion, okay, high runoff indicating about the high erosion. So that's why we find out this type of place is the high erosion or high soil loss. This is the river bank, we always find out that because you can see in the river bank area, so this is the river, so in the river bank area you can see the river bank, we find out the all places we find out the red color, okay. So it means that in the river bank area we find out the longer slope, okay, the longer slope or high slope, so that's the region it allow more runoff. So this type of red color, this type of place we find out the more runoff, and for the more runoff there we find out the more erosion for this type of river bank area. So that's the reason we find out this type of place have the high ls value, okay. And also for the steepness or steeper, so this type of red color indicating about the high steepness, okay. So high steepness it increase the runoff velocity, so this type of red color indicating about for this type of place have the high velocity of runoff, okay, high velocity of runoff. So that's why it show this type of red color place, okay. You can see all of red color indicating about the high slope. And the river bank we can easily get this idea more practically, because in the river bank we find out that high slope value, okay, basically longer slope we find out it's allow the more runoff, and steeper it also increase the runoff velocity, and more erosive power we find out for this type of place. So that's why it the more erosion we find out. So this is the way for the ls, but it also possible to use the arc map, and use this type of formula, and from the term we can also compute the ls or ls factor, but similar we find out the same result, okay, similar we find out the same result, if not much more difference. So this is the ls factor, okay, which is indicating about the topographic control on erosion. get topographic control on erosion, help of slope length and slope steepness. We can easily generate by DEM data for the LS. So now we talk about that C factor. Okay, we already know about the C factor. C factor basically it's indicating about that your ratio of soil loss under the specific vegetation to the to that of bare soil. Okay, so now we can easily identify the vegetation, and this vegetation we can suppose dense vegetation indicating about the no erosion, and bare soil indicating about the maximum erosion. So just estimate the vegetation indices from NDVI. You can use the Landsat or Sentinel, same process. So in this case, we try to keep suppose Landsat data, okay, because we take the 30 meter, and you try to keep the same resolution. It will be more better. Suppose in this case, we try to add the different types of data, but when you work with the real project for your research paper, then try to use the same scale value, okay, for the rainfall, then elevation, okay, elevation 30 meter, okay, you try to make the rainfall for 30 meter, okay, and also for the NDVI we try to use the Landsat data 30 meter, okay. So then we can find out the more better map. So let me open the Landsat data. And when you make the land use land cover, then try to use the Landsat data because it's also 30 meter, because we also need to use the land use land cover data set also. But for the C factor or cover management, we are just using the Landsat for making the NDVI or vegetation. Okay, let me just update that. I use suppose top of atmosphere reflectance. Okay, just copy. So just paste here. Then give a variable name. Put the variable name, suppose I put the name suppose L8. So now this image simply filter and create the composite. So just I put here dot filter bounds with my ARY, then put the dot filter date. Okay, try to keep the same annual or year 2017 1st January from, because I also take the data for rainfall data. Okay, put the same time period 2018 1st January. So I take this type of time, and also filter the cloud cover. So filter metadata for the cloud cover less than, I put 1. So now all of images, just I make the median composite and create the satellite images and clip with my study area which is RY. So now I find out my satellite images. So now what can I do? Just I make the NDVI. So take a variable. Suppose I put the variable name is the image NDVI. Okay. Call the L8 because it stored my image. I want to apply NDVI. So put here the normalized difference between two band, which is near infrared B5 and red B4, and put the rename. I put the rename as a NDVI. So now try to add the layer. So just add here map.add layer and call the image NDVI. Just copy and run the code. So now we try to create the another factor. It called the C factor. But we face a problem. This problem short because there is no image less than 1% for this time. So that's why we face this type of problem. So let's go try to increasing the cloud level. Suppose 10%. Okay, even there is no image. 50. Oh my god. cloud. Oh, sorry, I put the misspelling. So it's a cover. COV. So now let's check again for one. So I hope it will work now. So now you find out, if you want, you can also add here the color of NDVI map. So this is the NDVI map. So now from this NDVI, we need to compute the ratio of soil under the specific vegetation to that of bare soil. Okay. So let's go try to compute. Suppose here it's a NDVI. Okay. So now we try to compute the ratio of soil loss under the specific vegetation management to that of a bare soil, and range from 0 to 1. So 0 basically dense forest, no erosion. Bare soil, maximum erosion. Okay. So let's try to compute. So for creating this ratio, we just take a variable. Suppose I put a variable name is, we need the two value, alpha value and beta value for this. So just I take a variable, suppose alpha equal, I put the EE dot number, it's a number. I just stored the number in this variable, alpha value -2, and take the another value, it's a beta. This value EE dot number, this value is 1. Okay. So further we'll use the alpha and beta in our image of NDVI and compute the ratio between vegetation and bare soil. Okay, to identify. Take a variable. Suppose I put the variable name is the C1 and call the image of NDVI and then multiply with the multiply with alpha value and take the and this value we need to multiply, we need to subtract with one image. So I create a image, suppose take a variable, I put suppose one, suppose I put the variable name is the img and I create ee dot image. Okay, ee dot image 1 and I clip with ry. Okay, and now I simply subtract these two value, two images, c1 and image. So take a variable, suppose c2. So this img, this value subtract with this c1, not c1, this image NDVI. Okay, and this then further simply divide it. C1 basically compute the ratio, so further simply divide it C1 by C2. So take a variable for the ratio. I put the ratio, suppose take the variable name, suppose C3. Okay, and divided by C1 by C2. So C1 divide with C2. Okay, C1 divided by C2. Okay, and rename it as a C3. cover management. You can put anything. I put the C3. Okay, compute the ratio. And finally, take a variable, suppose C4. From the C4, we compute the C3, compute the exponential. So EXP, exponential, we compute. And now we compute the maximum value. So take a variable, suppose max C4. So I want to compute maximum value from here. Just take copy and paste. And then to compute the maximum value, so apply the reduce region. You already use a lot of time this function reduce region to compute the maximum value or average value, or so, and then put the here geometry, it's your ROI. Then reducer, apply EE dot reducer dot maximum value compute, and then scale the resolution. I put the 30 meter for land set. Okay, and others not need, just I try to print the relationship whatever. And let's print. So we find out this type of value 1.7. Then we try to compute the power management 5. So take the another variable, take a variable, suppose C5, and call the max C4. Apply the two images and then clip with our study area, which is ROI. And now also compute the minimum value. Okay, so take a variable, suppose mean C4, just call the C4 and apply the reduce region to compute the minimum value. Then put here the reducer. I put here EE dot reducer dot mean, and then apply the geometry basically ROI. Then scale I keep 30 meters. Okay, so now print. Okay, so now I print the minimum value. Okay, we find out this is the minimum, this is the maximum. Okay, so after that, for the cover management, so take a variable, suppose C6, and call the minimum mean C4. If you check the mean C4, okay, we just convert the two images and clip with our study area. So basically two image function, it create the image. So basically you can see it show the statistical value. This thing just show the statistical value, but now I want to convert this value, just display the image. So for that, just call the variable which is state to hit store it the minimum value, and then use the two images and clip with my study area, because I want to display the cover management map. Okay, so I put here ROI, clip with ROI. Okay, C6, and now take the variable, suppose C7, and simply make the subtract between the C4 and C6. Okay, C4 and C6. C4, this, subtract with C6. Okay, and also take another variable, suppose C8. So put here the C5, subtract with C8. And finally find out the create the ratio between the C7 and C8. So take a variable, suppose C. So C7, it's divide with C8. Okay, cover management 8, and I rename it as a C. Cover management C. So now let's go try to add the layer. So map dot add layer of C. And this value range, we know this cover management or C factor, this value will be mean 0 to 1. Okay, this is the range 0 to 1. Okay, for the cover management. Cover management set the value 0 to 1. 0 mainly dense or no erosion. 1 mainly bare soil or maximum erosion. So now run the code. Oh, we face a problem. This problem is okay. Oh, sorry, it's a C6. Okay, so you find out this type of map. So let's go at that. So we find out this type of things you can see. Okay, so 0 mainly dense vegetation. Okay, 0. Then 1 mainly it's a high erosion. So we find out this type of place or river side or river. We find out this type of place is the high erosion. Okay, based on the vegetation. So basically it compute the vegetation, compute the ratio of soil loss under the specific vegetation or management of that bad soil. So now range from 0 to 1 we find out. So 0 basically it also better. Suppose I just keep the 0 to 1, then check what happens. Suppose I put here that 0, or I put the custom value, suppose 0, put here 0 and 1. So this range mainly binary class 0 and 1 it create, or I just put the two color, it will be more better. Suppose red and yellow, green or yellow, we find out. So you can see find out this type of map. So now we find out this type of red color on this map indicating about the high erosion. Okay, and green color indicating about the low erosion. Okay, no erosion or low erosion, we find out this type of green color. But this type of red color indicating about the high erosion, this type of red color indicating. And suppose you can see also get some red color also this type of place. Okay, not much, but this is the red color. Also you can see this type of red color river bank, we find out the high erosion. But for the dense vegetation place, not much high erosion. Okay, so this it's called the C factor or cover management. Basically this is the ratio of soil under the specific vegetation of the bed soil, and range always 0 to 1. 0 mainly indicating about the dense vegetation or no erosion plus, 1 indicating about the maximum erosion plus. So let me import this color. Mm, or just I paste, just paste here. And put the layer name. Suppose it's a C factor. Okay, so C factor is done. So now this factor. Okay, so now we talk about that P factor. Okay, it's very important for the P factor. So for the P factor, it is also better. You try to make the land use land cover, okay, for your study area for the P factor or land practice factor. Okay, land practice factor. So for the P factor, suppose in this case you can simply make the land use land cover using Landsat image, because we try to keep all of satellite source 30 meter. So try to use the Landsat image and then use. Okay, so for the P factor in this time, that is okay. So I try to use some ready-made land use land cover data, but when you work with own study area for your own project or research work, try to use the your land use land cover. So simply make the land use land cover for your study area and classified, suppose bare land, build up, vegetation. So this type of class simply classified, and then we simply work with that. Okay, for the land use land cover. But in this case, I simply take the one data set. I use suppose modis LULC. Okay, and then make the land use land cover for my study area and make the work. But when you work with the main work for your research paper or presentation, try to use the land set image and make the land use land cover. Okay, next I try to use some LULC. You can also use the dynamic, no problem, but I try to use suppose land use land cover from the modis. Okay, just click on the modis. We try to use, you can see the yearly, it provide the yearly land use land cover data. So and we use it. Okay, and then paste here. So now take a variable. Suppose I put the variable name is LULC. So I just put that select the band of the modis land use land cover data set. We find out the band name is okay, this band name is okay. They also changed the band name. This is the band name, new band name, majority land cover type 1. And this band is stored, you can see which type of information. Majority land cover type 1, it's stored water body, then evergreen leaf forest, broadleaf forest, deciduous forest, mist forest, close shrubland, open shrubland, woody savanna. So all of class including in this band. So just I copy the band. And this data set is available from, you can say, 2024-01-01. This time we try to use it. Just paste here, and then put the filter date function. So I take the annual from year of 2017 from 2018 1st January. So I take the 1 year. Okay. So for the 1 area, I find out the 1 image. So I put the first function, no problem, because for the it's provide the this data set annual. So for the 1 year, I found the 1 image, and then just click with my study area. This is RY. If you want, you can also display the land use land cover map. Just use air map.dat layer and add the LULC and run them. So now we find out the LULC. So when you work with the p factor, we need to combine the LULC and slope in a single image. Okay, because in the p factor we try to identify the slope value based on different types of land use land cover data. Okay, based on land use land cover data. If you check, suppose for land practice, okay, where is the website? This one. If you check the, so you can see the C factor land cover classes. So this is C factor for different land cover classes. LS will already work. So S, this one, practice factor for P factor. So you can see it sets some slope and also put the value. Okay. Suppose from this range it set this type of value. From this range it set this type of value. So now we set some value based on our class, land use land cover class, and set some value, slope value. Okay, and make the practice or P factor. Okay, so for the region we just simply combine LULC and slope together. Okay, so LULC, this is the LULC, we just simply add the combine. So combine LULC and slope together. Okay, so take a variable. I put the variable name, suppose LULC and slope, and then call the LULC add bands with slope. I already make the slope. Okay, so you can see. Okay, so we just call the slope and paste here. So now slope and LULC make the one, combine these two things. So now further from here we simply create the p factor map using expression. So p factor map using expression. Okay, so this factor value I simply copy from my another code and then paste. Suppose I already have here, so p factor I simply put this type of value. Is it? Yeah, this one. Yeah, this type of value. Just I copy. Then I explain the code. So I paste it. So in the p factor, what happened? You can see. So we take the LULC 11. 11 basically one kinds of value. Your land use land cover value. Then suppose 11, then 13, 14. Then you can see we take only for the 11, 11, 13, 14. This type of value, and if you check this type of value, which class store it, so you can easily get the information from our data set. But when you work with land use land cover, we set 0 1 2 3, suppose 0 for vegetation, 1 for, but in this case we take the data set from the modis. So that's why you can see 11, then 13, then 14. Also you can see the 12. Okay, also you can see the 12 we set different value. Okay, so different classes. So for that you can see the data set from the annual. You can see 11 is the permanent water. Okay, so for the permanent water we set a value for slope. Then 12 is the cropland, we set the value for cropland. 13. Okay, then you can see that 10 is for grassland, 9 is for savanna. Okay, so we simply check this type of land use land cover practice area from this level. So this is the value. So we simply set this type of value and set the slope value. You can see we simply set this type of value. Also you can see combine slope. Okay, slope, we find out the slope value less than 2% and land use land cover equal to 12 or land use land cover 14. So if the slope value less than 2%, then this land use land cover we find out the suppose agriculture or for 12 and 14. So what is the 12 and what is the 14? So you can check what is the 12 and 14. 12 basically cropland, 14 is for cropland, also natural vegetation. Okay, cropland and natural vegetation we find out. So if the slope less than 2, then we find out this type of practice or this type of land cover we find out. Okay, just use this type of things, combine slope, and also you can see if the slope is okay, less than 8%, then we find out the 12 and 14. Okay, so basically land practice we are just use only for only concerned about that your cropland or vegetation area, okay, or water body. So this type of things we are just simply concerned for the land use and land practice. Okay, agricultural land, then cropland. Okay, we simply add in here and simply set some value. Okay, and it's a p factor which is indicating about the land practice. So now further we try to add the map. So just run the code. Oh sorry, this one, this our code. So run the code, click with ROI. Okay, we need to change the band name, but previous time, okay, now available LULC did not match any band. We have to use the new band, majority land cover type 1 and slope. Okay, so this type of LULC, this is the new band name. So now I find out this type of p factor, you can see, and you can see we face this type of problem. It show the grid or cell, because in this case I apply 500-meter data set for land use land cover practice. So when you work on the real project, you try to make the land use land cover for your own study area. Okay, suppose you just classify different land use practice, land use land cover, different classes. Okay, water body, cropland, agricultural land, vegetation, then also a build up area. Okay, then you simply set the value, okay, for the slope value. Suppose distance to distance of slope, if the slope less than 2%, then I find out this land I find out. So you can also just add the slope map. Suppose just overlay the slope map and also check from the inspector tab this type of, suppose I know it's a water body, so I need to check for the water body what the slope value I can get. So you can simply click on here. Suppose this is the water body, so now for the water body what the slope value we can easily find out. You can see 0.4, so I simply use it. Okay, if the slope value 0.4, then I find out this land use land cover classes and just add the expression and add this type of requirement one by one. So now it create the p factor, okay, or land use practice factor. Okay, so now creating all of factor. So now we simply multiply all of factor together, and it called the estimating soil loss. So we just apply the formula. Okay, this formula I just take a variable. Suppose soil loss equal, and it's a image. So put here ee dot image and multiply all of factor. So just call the r factor. This r factor multiply with k factor multiply with ls factor multiply with c factor multiply with p factor. Okay, 1 2 3 4 5. Basically this 5 factor we are just use, and I rename it as a soil loss. So now we try to identify. Just take a map dot add layer. Suppose map dot add layer and call this soil loss and run the page. It's a capital P. So we find out this type of map, and further we try to add the color soil loss, just spacing suppose 98%. And further if you want, you can also make the classification. Okay, suppose I just add the color, suppose low soil loss through this type of blue color, greater than this type of green, or any color combination is simply set, then yellow color, and high soil loss estimation this type of red color. Okay, so you find out this type of map. Okay, or if you want, you can also add the another color combination, also stressing, suppose 3 sigma. Okay, all those suppose 90% check. Okay, so we find out for this type of place or river bank, we find out the high soil loss estimation. Or if you want, you can also make the class. Okay, suppose I want to make the class, I simply set some range, and then I simply make the class for the soil loss. Okay, and this unit is the ton per hectare per year. Okay, for the RUSLE model, unit is ton per hectare per year. So let's go try to make the class. Total suppose 5 class we try to create. Or if you want to download the GeoDip file format, also work with the ArcMap, but we try to make the class. For the class, suppose I just make the one class. Suppose for the one class we simply set less than 5. Okay, we make the one class, then we make the another class, or less than suppose 10, then we put the 10 to 20, then another class suppose 20 to 30, then suppose 30 to 40, and greater than 40. So I create this type of class. Suppose it's just name the, it's I put it's the name for slight, then suppose it's for moderate soil loss, so moderate region. This region I put, suppose it's a high, then put here, suppose this region it's very high, and it's the, we consider it's a server. So now I want to apply this type of classes. So let's go to apply. So take a variable, suppose soil loss class. Well, this classification is also possible. You simply download the geotip file and make the arc map, and also possible. Just simply reclassify and set the this type of range, and then also make the classification. But it also possible to use the Google Earth engine. So in the Google Earth engine, I want to apply just I call the soil loss and apply the expression. So I put the expression I create total 5 class. 1, 2, 3, 4, 5. Yeah, 5 class I will create. Suppose I put here B mainly band. Okay, so this B it means the band. So I simply choose the band name. I choose the band name from soil loss. This is my band name because I put the band name is, you can say I put the rename, so it's my band name. So I simply set that band name because this band is stored the information, this type of soil loss information. I simply paste here. Okay, simply choose the band soil loss and then put the range, suppose less than 10. Okay, less than 10. Close the bracket and also start the bracket. Okay. And then put the sign and put the class number. I put the class number is 1, first class. Okay, then put the plus sign and then put this symbol again, and then same process, just apply. Just I copy the same line of code. And paste here. Okay, so I put the another class, suppose this is the 20. I put the another class for 20 and put here the plus. So this is another class I put here, it's a 30, third number class plus. So then put here the 40, fourth number class. Okay, and all of the greater than 40. So for that we simply mention in here, just put the class number, then it automatically take all of value less than greater than 40 and create the class. Okay, and then simply put here the dot rename. I put the rename, suppose it's a soil class or S class. and clip with our study area, which is RY. So now let's check the result. So I add the map dot add layer and call the soil loss class and put here that mean. It will be start from 1 and max up to 5. And you can put the different types of color. Okay, I add the color later just on the code. Okay, it should create this type of. So I will add the color. Suppose for the slide level, I want to use this type of blue color. Then moderate, I want to use suppose this type of color. Then high, I want to use this type of color. Then suppose very high, I want to use this type of yellow color. And extreme, I use this type of color or this type of red color. Okay. So now apply. So now you find out this type of things, but this classification is also more better if I just load the value also. Okay, suppose I will start from the less than 5 then 10, so then I hope it will be look more perfect. So now again, so it show the maximum place. We find out the class 1. Okay, you can see class 1 mainly. We find out that less than 10 ton per hectare per year, this type of blue color indicating. Or you can also keep this, no problem. So I put, suppose it will be less than 5, we consider. Then we put here the 10. Then I put here the 20. Then 30. So now let's check the result. So now we set the slide less than 5, moderate 10 to 5 to 10. Okay, high 10 to 20, very high 30 to 40. So let's go try to check the result and add the color again. So now we find out the more variation. Okay, when I decrease the value, we find out the more variation. Suppose just I add the suppose less than 5, we set this type of color. Then 5 to 10, okay, let me check. So we set the range. It will be first one is start from less than 5. Okay. Then second we set the 5 to 10. Third we set suppose 10 to 15. Okay. Then fourth 15 to 20. So then we find out the continuous, increase the 5 ton. Okay, then I hope it will be more better. And finally we set suppose greater than 20. So we set this type of range. So we set here suppose less than 5, then 10, then it's 15, then 20. Okay, and last class is all of greater than 20. So it will look more perfect. Friends, so increase the 5 ton by 5 ton. So now I set the color, suppose for the slide this type of color. Then moderate, we use this type of color. Then high, we set this type of very high, and then sever or string. So now I find out this type of map, okay, for the soil erosion, so we can easily identify, okay, where is the slide, where is the moderate, where is the high, where is the very high, and where is the extreme soil loss based on the range. Okay, just import, just copy and set the visualization. Or if you want, you can simply click on the pen sign and copy the all of color, and this color simply set here. Just use the plate and then make the list, set. So now this color is automatically set. Okay. Oh, maybe it's a problem. Oh, we need to put the quotation for every color. The quotation. Okay, and I put this is the soil loss map. Okay, so after creating the soil loss map, then we need to compute the soil loss average. Okay, for annual average, we try to compute the soil loss for the annual average. So for this basin, we try to compute the average soil loss estimation annually, annual average soil loss estimation. Okay, so let's go try to compute average soil loss estimation. Okay, just we'll make a break for 10 minutes, then we'll start again. Okay, just a break for 10 minutes. Okay, welcome back. Can you hear me? Okay, thank you. So let's go continue. Okay. Okay, so now we try to compute the annual average soil estimation for our soil map, soil loss map. So it's very easy, just take a variable. Suppose I put the variable name is annual soil loss mean value. We try to compute. So just call the soil loss. We already make the soil loss this one. And then apply the reduce region. Okay, and further apply the reducer dot reducer sub dot mean to compute the average value. Geometry, it's your shapefile ROI. Okay, make the dictionary. And the scale is equal to the 30 meter, can compute the result. So print annual soil loss mean. Run. So further we can simply get the result. Okay, so for this basin we find out the annual soil loss 32.686 ton, okay, per hectare per year. This is the unit for this soil basin. And further we simply export and then work. Okay, so now this is the way we compute the soil loss estimation using RUSLE model. But when you work the real project, we need to add the more accurate data. Okay, we need to add the some all of high resolution satellite data and produce same step, just apply and then produce all of factor, then simply multiply, then we can easily get the result for that soil loss estimation. Okay, so now I hope you also get the idea. So I can find out the lot of paper they are already work with the soil loss estimation using RUSLE model. So you try to read this type of paper and further simply choose your own study area, and then you can also make the scientific paper for your own study area for estimating the soil loss estimation using the RUSLE model. Okay, so it's very common topic in remote sensing to identify soil loss estimation using RUSLE model. So I hope you can also do it easily, okay, for use of RUSLE model. Okay, and then all of layer we can easily export as a GOT file format. Okay, and further we can also use the ArcMap software to produce our map. Okay, so now we talk about the another topic for the change detection, for the NDVI change detection. So previous class we discussed about that your NDVI vegetation trend analysis, we discuss about that. But now today we discuss about that how we can easily make the change detection of NDVI, and then make the change detection, calculate the area. Okay, and from the change detection we also try to identify for the positive change or negative change or unchanged. So this type of things we can easily get the idea. Okay, or okay, and also calculate the transition. Okay, this type of things try to discuss about that. I guess this is the NDVI class. So let's go. Let me. Okay. So first of all, I try to show you this type of process using the manually, how we can easily do help of ArcGIS, mainly ArcMap tool, and then create. Then further, I also discuss about that code. Okay, so let's go. Let me share my screen. Just a minute. So I need to calculate the land use land cover for the different time period, as well as also land use NDVI, okay, for the different time period. Okay, otherwise all as well as also satellite or precipitation. Okay, so all of those simply apply for the different time period. For the land use land cover, take the data for the different time period, and then also take the data for precipitation for the different year. Okay, and then apply the same process to make the temporal analysis of the soil loss estimation. Just simply change the factor, all of factor for the annual factor. Suppose to land use land cover, then annual precipitation. Alright, and then I hope you can easily do it for same process. Just simply change the year, all of year can really work. So here I already exported to decade NDVI map. If you check, so this is the result.